Okay, now we're going to look at section 1.5, and we're going to continue working a little bit with slopes, some quite familiar and some new stuff. So the first thing is parallel and perpendicular lines. I'm hoping that you remember that when you have parallel lines, the slopes of parallel lines are the same. So the slopes are the same. In other words, the slope of the first line equals the slope of the second line, m sub 1 and m sub 2. And if we have perpendicular lines, the slopes are opposites and reciprocals. So the slope of the first line is equal to the opposite or negative of the reciprocal. Hopefully this is something that you remember, and you will be asked in your homework to take a look at some of the a couple of lines and look at their slopes to decide if they're parallel or perpendicular lines. Another way of looking at slope is discussing the fact that it is a rate of change. The slope of a function that has units can be considered not only a slope, but a rate of change. So for example, if I have a function that is represented by miles being compared to hours, and I want to find the rate of change from one point to another, we can use the secant line, and the rate of change, or the slope, from one point to the other here, in other words, my delta y over delta x, delta y is going to be my y value, or miles, and delta x is going to be my x value, or hours, or in other words, miles per hour. So the change from point A to point B, called the rate of change or slope, can be represented by a units called miles per hour. So although rate of change is exactly the same as a slope, sometimes it can be found when we have a curve. So the rate of change of a curve from one point to another gives us the average rate of change. We'll talk a little bit more about that in a second. The big idea here is that my rate of change, since it's measured in units, since my slope is measured in units rather, we can consider it a rate of change. If you look at page 197, this is shown quite clearly in the blue box, and they use function notation there. So they're looking at x sub 1 and x sub 2, and therefore the ordered pairs x sub 1 comma f of x sub 1 and x sub 2 comma f of x sub 2. We can also look at this with a little different notation when we look at the rate of change from x to x plus h. So now, instead of labeling these 2 points x sub 1 and x sub 2, I'm going to label them x and x plus h. Again, my ordered pairs in function notation would be x comma f of x and x plus h comma f of x plus h. And if I wanted to find the average rate of change between these 2 points, I would again go to my change of y over change of x. In this case, my change of y is f of x plus h minus f of x, and my change of x is x plus h minus x. This should look fairly familiar to you. If I simplify f of x plus h minus f of x over h, this is the difference quotient that we looked at a few sections ago. So just changing our notation a bit, instead of calling this x sub 1 and x sub 2, if I look at the point x and another point that is h units away from it, we can find a slope or a rate of change notation that looks just like our difference formula. If you'll move ahead now and take a look at page 199, we'll talk for just a minute about average rate of change versus instantaneous rate of change. You can see that they have a diagram of a young man and his growth chart, and they want to find out how fast is he growing at a particular point P, or how fast was he growing at a particular point P. Well, you see that if we can take point P and another point D, I can find his average growth rate over this period of time. Now he's not, let's say his average growth rate here is, I don't know, 3 inches per year. Now, at every point in time, he is not growing at exactly 3 inches per year. He's growing a little bit faster here, maybe a little bit slower, a little bit faster in this area, maybe a little bit slower in this area. But over this span of time, his average rate of change can be calculated. If I bring my points closer and closer to the time when I am looking at, I can take 2 points that are very close to each other and begin to approximate the instantaneous rate of change. And if it were possible to do a slope when the value x is only 1 point, although I can't because the denominator would be 0, but if I could find a slope with only 1 point, I could find instantaneous rate of change. The best I can do really is to find the rate of change over a very short span of time. Read the description by that picture on page 199 to understand this a little better. We'll talk about it in class. But if I could manage to calculate the slope at exactly 1 point in time, that would be the instantaneous rate of change. This is actually something that you will learn to do in your calculus class. For now, however, we'll stick with our average rate of change, where we are taking 2 values, finding the slope of the secant line to find the average rate of change over that period of time. A specific rate of change is called average velocity. This has to do with any function that expresses an object's position, which we call s of t, in terms of time. In other words, the average velocity from t1 to t2. So again, back to our miles per hour. If I have a time and I have some position, usually denoted by s of t, I can find the average rate of change over that period of time. And since my units here are going to be something like miles per hour or feet per second, we can call it an average velocity. This concludes section 1.5. So please make sure that you go back and fill in any notes. Take a look at the book for some examples if you have areas that you don't quite understand, and come to class prepared to ask any questions regarding the lecture notes on these sections.